Hormones, hormones, hormones here and there. Hormones, 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 hormones everywhere. Well, there's hormones in the thyroid for our metabolic rate, and gonadotropins that help females ovulate. There's hormones in the kidney, and there's hormones in the brain. Hormones help us sleep at night and wake up again. Hormones, hormones, hormones here and there. Hormones, 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 hormones everywhere. Hormones, 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 hormones everywhere. Hi, we're going to do a new topic today. We're going to talk about ovulation, the remarkable process where an egg kind of matures and gets ready to be fertilized. And so actually, you can say the very beginning of life. What could be more refreshing and with this joyous time than the beginning of life? So let's take a nice deep sigh of relief and see where we are in the course. So if we think of this course as an arc covering the principles of hormone circuits, where the goal is at the end, when you take a biological system, a physiological system, you'll know how to think about it with simple mathematical models, and that'll help you ask new kinds of questions and do new kinds of experiments to understand the principles that unite different body systems. If you're feeling you're coming closer to that goal, then this course is working. And in the course, we started off with the leptin circuit. It's kind of a simple set point or operating point, the intersection of two operating lines, and saw how the set point can change a lot between people and over situations. Then we went to a tight control circuit, the glucose insulin circuit that keeps 5 millimolar glucose, and saw a principle where cell size control can change, cell mass can change to buffer changes in things like insulin resistance, and how that breaks down. We talked a lot about transitions to diseases as bifurcations. That's when some fixed points disappear and new ones form. That's also a theme with depression. You remember I talked about depression, where too much stress makes you jump to a fixed point of a large adrenal and small hippocampal activity. We talked about the HPA stress axis. And today we're going to continue with this HP axis, the hypothalamus pituitary. It's actually amazing, the hypothalamus and pituitary. The hypothalamus is the brain region that controls a lot of signals, and the pituitary is its helper to send those signals chemically to the rest of the body. And through the HP axis, the hypothalamus pituitary, different kinds of hormones control some of the most fascinating things about our mammalian life. For instance, growth, stress, that's the HPA axis, thyroid, which is metabolism, and today's star, reproduction. And that's the ovaries, or in males, the testes. So we're going to talk about the HPO axis. And it's really interesting. Why is it one axis, one kind of set of glands, hypothalamus, pituitary, control these major tasks of mammalian life? Maybe there are trade-offs between them. Indeed, if the pituitary is in trouble and starts being destroyed, there's a certain order in which the body turns off these functions, growth and reproduction, before metabolism, and last of all, the stress axis, which is so important to help us wake up in the morning. So there's a kind of body conservation of tasks if the pituitary is sick. So we focus on the HPO axis, and this lecture is going to be like a different principle and different way of thinking. So mathematically, I think it'll also be refreshing. All right, so what is the problem we're going to consider? We're going to consider, there's many things about reproduction and ovulation to talk about. We're going to focus on one kind of puzzle, and that puzzle is the following. Every menstrual cycle inside the ovaries, there's about 20 new ready-to-go eggs starting to, or what's called follicles. So we'll discuss that. So it's an egg wrapped by some support cells that start a race. And in human beings, it's only one, usually, that gets to ovulate and get a chance to meet the sperm, get fertilized, and make a baby. So it's a choose 1 out of 20 race. And the question is, how is this one chosen? The 10 to 20 follicles raise, they grow, one chosen in humans. In mice, it's also a large number of follicles start, but 6 to 8 are chosen. So mice have a live fast, die young, leave a lot of baby strategy. Bats and elephants and whales take care of usually one offspring, sometimes twins. Other animals, as you know, like the dingo makes 3, right? Some esoteric reason I'm telling you this fact. Animals can have 2, 4, 4 to 5, 6, different numbers. So it's for those computer scientists, it's kind of a choose M problem. N follicles start, you have to choose M out of them. How do you do that? That's our question. And so in order to understand, first I want to say that this choice is very important, very critical for evolutionary fitness. And that was shown very elegantly by an experiment in the 1940s by a scientist called Lack, who took nests of birds in the forest near Oxford and manipulated the number of eggs in the nest and asked how many birds survive, fly out of the nest. So this ovulation number is important for fitness because if this is the number of eggs, 1, 2, 3, 4, 6, and this is the number of surviving offspring, the more eggs, the more surviving offspring, of course. But above a certain number, start to drop. Why does it start to drop? Because in this region, there's more parental cost. So the mama bird, papa bird are bringing more food, they're exhausted, and the chicks just don't survive. So there's an optimal size. And that size, by the way, is the average clutch size for that species of bird. So it's a way to show that, to argue the natural selection brings this choice close to the optimum. And since there are a lot of experiments, like if you can manipulate parental costs, does natural selection push you to higher optima? And the answer is yes, etc. So it's a pretty well-supported theory in evolutionary ecology. So let's agree that this number is different for each species. So bats, for example, have to carry their one baby 40 kilometers to teach them where the particular fruit tree is that they go to again and again. Bats live for 40 years. They take care of one child, teach it a lot of that. And mice, as I said, it's better for them to make a lot because anyway, their average survival is 1 year before an owl eats them or something like that. They make a lot of babies, and there's a whole spectrum of life history theory about that. So let's agree the ovulation number is important for evolution. How can you have a system inside a mammal that can tune this number and reliably choose one or whatever out of a large number of follicles is the question. So I'm going to stop now until there's a question. So now's your chance to chat. Chatteroni. Oh, Ofer Kapp says, is there a division of labor within the pituitary with these different functions? And Michal Shilo, by the way, I'm going to talk about Michal Shilo's work today, unpublished work by Michal Shilo. In her master's thesis, she really cracked this problem wide open. Congratulations, Michal. And she says different cells in the pituitary are responsible for different axes. In our case, it's going to be the gonadotrope cells in the pituitary. They're making the gonadotropins that make females ovulate. Remember in the song? And All right. And this is your time to chat a question. I'm sure you have some question. I'm sure you're curious. Why don't you chat me a question and I can see if I'm clear. All right. Now, let's talk about how ovulation happens in the female. So the HPO axis, we have the hypothalamus in the brain, secretes an enzyme to the pituitary. That enzyme is called gonadotropin releasing hormone. It's released in pulses. In children before puberty, it's constant. Then it starts making pulses. And that's actually a signal for the start of puberty, all the hormonal changes, et cetera, that have to do with puberty, GnRH. And then pituitary secretes the gonadotropins, the famous gonadotropins called LH and FSH, follicle stimulating hormone. That's our X1 and X2 from the classic HP models that we're talking about. And here we're going to the ovaries, right? Ovaries. And let's see what's going on in the ovaries. So the ovaries are almond-sized, 2 almond-sized organs. There's on both sides of the uterus, rechem. Yeah? And inside these ovaries, we have the very precious cells that are going to become a new baby. They're called oocytes, and they're surrounded by support cells, as I said. So the unit we're going to talk about is a follicle. So inside the ovary, there's a follicle. The follicle is made of the egg that has the DNA, one copy of the 2 copies of DNA that's going to become a baby, and it's surrounded by support cells, G cells, and T cells, called granulosa and theca. Those names are not so important, called G cells and T cells. And this unit here is a follicle. Now, when females are born, they have about a few million follicles. I mean, during embryo, these die off, and when you're born, you have about 1 million, and then it drops exponentially, actually, and you run out around age 50, which is menopause. So for some reason, those follicles die a lot, and your supply of follicles runs out around age 50, menopause. By the way, humans are among the few species that live a long time after menopause. So there's what's called fitness advantage for being a post-reproductive female, apparently, sometimes called grandmother effect, aunt effect, something like that, increasing the fitness of... there's different reasons for that. You can try to think about that, and there's papers about that if you're interested. All right, so this is log number of follicles. It drops exponentially over time. But every menstrual cycle, that's to say every 28 days on average, there's about 20 follicles that enter a kind of race. Right? So inside the ovary here, there's 20 follicles. When I say 20, it could be 10 or 15. The number can be different from different women, but it's a large number compared to 1. So they start off very, very tiny, and over several months, some follicles die, but some begin to grow, mature, and grow, and start here at the size of 2 millimeters, which is a huge, actually, for biological kind of collection of cells. So the 2 millimeters, this is at the beginning of the menstrual cycle. So let's talk a little bit about the menstrual cycle. Talk a little bit about the menstrual cycle. What did I do here? I messed up my menstrual cycle. Okay, so this is day 1, 2, 3, 4. Here there's 5 days of bleeding, where the lining of the uterus goes out, and day 14 there's ovulation. And then there's another 14 days on average of what's called the luteal phase, where the ovary builds up its capacity. And if there's no implantation of a fertilized egg, there's bleeding and the cycle starts again. This, by the way, this 14 days, this part is very constant, 14 days. And this can change between one female and another. It could be, the whole cycle could be 35 days or vary, but average 28 days. So we're going to talk about this part of the cycle. From the beginning to ovulation. This will be our race. Right? So day one, the race begins with a large number of 2 millimeter follicles. And they start growing, okay? They start growing. And some of them die. And then they continue to grow until there's just one 20 millimeter follicle at around day 14. And then this follicle merges with the side of the ovary and causes an inflammation process that ruptures the ovary. The DNA carrying oocyte with some granulosa cells goes out into the uterus. The remaining granulosa cells form an endocrine body that secretes progesterone, and that starts this side of the cycle. So this is the winning ovary, the winning follicle. The winning follicle. The follicles themselves, these granulosa and theca cells, they're a powerful endocrine gland. They become a very important gland in the body because they secrete a very important hormone that we all know about. This hormone is estrogen. So the follicles secrete estrogen. I'm going to call it E2 from now on. That's like the official name. And estrogen, just like in all the other HP axis, shuts down the production of LH and FSH and GnRH. It shuts down the above ones, right? So X3 shuts down the production of X1 and X2. So it's a similar way of thinking, all these HPO axes, but each one has its own design and its own purpose. Stress axis acts to, all these have this acute stress, chronic stress, this biphasic effect of cortisol and mood swings and all this stuff. Here we need to run a cycle. So we have estrogen, and the way that estrogen is made is important for our talk. So I'm going to look inside this follicle here. These theca cells, they have receptors for LH, and they make a steroid that's called androgen. This androgen is converted by granulosa cells under control of FSH into estrogen. Right, so this androgen is an intermediate between theca cells make androgen, granulosa cells converted to estrogen. These details are going to be kind of important for this race, as you'll see in a second. And the estrogen shuts down the FSH. So it's kind of so we have here FSH is like follicle stimulating hormone, is driving this race. The bigger the follicles are, the more estrogen they make that shuts down the FSH. I just want to say that ovulation happens when the follicles are so big that they make so much estrogen that this negative effect now becomes a positive effect. So estrogen is, the HP ovary axis has a special feature that the X3 starts at very high levels to activate LH and FSH. And this creates what's called the LH surge. So LH suddenly goes up really high here, and that signals this ovulation. And then progesterone on this side, and if there's no fertilization, the uterus, there's bleeding and a reset. New follicles enter, race, one of them wins, LH surge. So, any questions? I see there's some Chatteroni questions. Ran Ashkenazi, do some species have different shape for the surviving offspring versus number of offspring, more than one peak? So Ran is asking, in this lac clutch plot with the maximum, do some species have multiple peaks? Great question. I mean, it could be like in different conditions, you make a few or many babies, really interesting. Ophir, are all of the NO sites wasted in each cycle? So all of these N, let's say call it N beginners, all but one in humans or all but 6 to 8 in mice are wasted, which means they're go artresia, which is a kind of apoptosis, cell death. And most follicles undergo cell death, and nobody knows exactly why. Maybe it's a kind of quality control. Because again, if you win the race, it maybe means that you can't be too mutated in your ribosomes or in important things, right? If you win the race, it means you've done something. It's like you passed an exam or something. The sperm also have a big race. They have to come. So it's a big selection process. It's amazing when you think what it takes for a person to be born. It's like, it's a 1 in a million. You can't imagine. It's so many things have to happen right. Okay, so why can't the mechanism just be random instead of chosen? Each potential egg having an equal chance. It could be also a random thing. It could be a chance thing. What I want to say is that this race has to be dependent not just on the properties of each follicle on its own, but on a communication between them. And this communication has to be through the HPO, or the blood anyway. How do I know that? You have 2 ovaries, and follicles start in both, but only one ovulates. Sometimes it's this one, sometimes this one. If you have if there's a medical reason or some reason you lose one ovary, ovarectomy, you lose one ovary, the other one ovulates, also only one, but twice. It basically, every month it ovulates. So there's still a race there, but if before they were racing in 2 ovaries, now they're racing within 1 ovary. And that tells you that there's some systemic factor, systemic through the circulation, that's controlling this race. It can't be just something about each follicle on its own. Does that make sense? Okay, Michal Shilo, by the way, is answering. So great. You have the author of this research answering your chats as you chat them. So please use this opportunity. Michal says that it's true that usually these are not equal sizes. Generally, it's the biggest one at some point that wins. That's generally what's observed. So it's something about the size is important, the initial size. Yeah, good point, Michal. Okay, so we want to understand who's going to win and how does this work. And it's a very, very important problem. Let's take a nice deep sigh of relief. I just want to talk about ovulation. Follicles compete. The cycle just repeats. Well, I've played all my cards. and so have the other follicles. Nothing more to say, no more FSH. The winner takes it all, the loser standing small. Besides the victory, that's her destiny. The winner takes it all, the loser standing small. So how does it happen? In order to figure it out, there's no other option but to use mathematical models. We're not the first. People have been wondering about this for decades, and I want to mention the pioneers are Lacker and Peskin in the 80s. They wrote a really beautiful mathematical model that explains how this race is won. And it was a mathematical construction, and there wasn't a physiological basis for it. And what Michal did was find a physiological basis that produces a mathematical model of the same class or family as the mechanism of Lacker and Peskin. It's not the same as Lack. It's Lack for the clutch size, the eggs, and Lacker for the model of ovulation control. And I want to present that model to you. So if we go back to the Zoom, what are we going to do? We're going to, our variable is going to be the size, xi is the size of follicle I. Follicle I. Okay? So we have, in the beginning, I is 1 to n. Let's start the race. x1, the size of follicle 1, x2, the size of follicle 2. And if you do ultrasound at these different days between 1 and 14, you can see the follicles, and you can measure their size, and that's often done actually in fertility clinics, etc. And when you measure the size of these different follicles, what you observe is, so this is time, day 1, day 14, and this is the size of different follicles. Is okay, they start at different sizes. Let's start, this is day 1 here. They start at different sizes. And then generally the largest one, but not always, grows. And in fact, it grows linearly with time. And that's unusual for cells. Usually cells grow exponentially. These are follicles, right? So follicles, follicle size. And the other ones eventually die. So this is the kind of dynamics we want to understand. So we're going to write an equation for the rate of change of the size of follicle I. And of course, it's going to be like all cell things. Cells come from cells. So the xi dt has to equal xi times the growth rate, like all cells. Because more cells, the more cells are going to be made in the next time point, because there's a proliferation rate per cell. Now, another thing we need here is to take into account that FSH is the driver, is the hormone, follicular stimulating hormone. I mean, after all, it's the one that makes them grow. So our first task is to see how much FSH there is. Remember, FSH is secreted by pituitary, and it's inhibited. I mean, during this part of the cycle, it's inhibited, before the LH surge, it's inhibited by estrogen. So FSH is inhibited by estrogen. So we're going to write it like this. The more estrogen, the less FSH. How much estrogen is there? So estrogen is secreted by the follicles. So estrogen is something like the sum of all the follicle sizes, because the bigger the follicle is, the more estrogen it makes, the more cells it's here. And we're going to call this sum X total. This is going to be important. This X total is the total size of all the follicles at a certain time point. So FSH goes like 1 over X total. More follicle mass total, more estrogen, less FSH. And therefore, we get the interesting equation, dxi over dt is xi over X total. So that is to say, it's the relative size. That's interesting already, isn't it? It's the relative size. It's not how big you are, it's how big you are with respect to the others, right? So familiar from jealousy in normal life, right? You look at the others, you measure yourself relative size. So follicles do that too. Relative size. All right. But that's not enough, because if that was all, each follicle still has a positive growth rate. They all grow. But we know that at some point they stop growing. So we need to add something else. This is the Lacker's insight. We need to add another function that will make follicles die if they're too small or too large. And that means we need to look for a biological material in the follicle system that makes them grow and also makes them die. That's not FSH, it's not LH, it's not estrogen, but there is one thing like that. That's Michal discovered. And that one thing is androgen. How did she understand that? She used a very common information about a very common medical disorder in females. And that medical disorder is called polycystic ovary syndrome, PCOS. And it's very common. I mean, on the order of 10% of women diagnosed with PCOS. And a lot of times it doesn't cause terrible fertility problems. Sometimes it can cause a lack of menstrual cycles, a lack of fertility, problems with fertility, and additional problems. And one of the things that happens often in PCOS is that our ovary is filled with these cysts, which are actually large, stuck, like large follicles. They're not ovulating. And when you look with ultrasound, what happens is actually they large and then they die. And another large one comes. It's kind of a cycling of these large, but something is wrong with the race, right? You want the winner to take it all. But here it's like many are standing kind of small, but nobody's taking it all. Nobody's daring to take it all. So this is PCOS. And PCOS has different reasons, but the one thing that's critical, actually it's the criterion for PCOS, is high androgen. And that sometimes causes a hair growth in the chin, and like androgen is, andro is male. It's a kind of a male, it makes some male characteristics. So high androgen interferes with the race. It's bad for follicle maturation. On the other hand, so high androgen somehow is bad for maturation, for ovulation. But on the other hand, low androgen makes follicles grow. So it's a biphasic thing, low androgen. So the follicles have androgen receptor, and you need the androgen receptor in order to stimulate follicle growth. But too high androgen is bad. So does that remind you of something? Does it remind you of glucotoxicity? Glucose makes beta cells grow and then die. It's the biphasic effect. So we're going to put here androgen. This is this function. It's biphasic. And I'm going to propose to you that it's actually so this androgen is a private thing. It's made inside the granulosa cell. So the theca cells on the outside make the androgen. Some of it is secreted to the blood. Some of it goes inside. The bigger the follicle is, the more androgen is inside. So the androgen of a specific follicle, I'm going to propose to you, is the critical element in this race, where if the follicle is too large, has too much androgen, it's going to die. If it's too small, too few androgen, it's going to die. Only the ones in the middle are going to make it. So, and to finish these equations, we just need to understand how much what is androgen in each follicle. By the way, I hope I'm making sense. I'm going to just look at the chat here. Nobody's chatting. I imagine you're sitting at the edge of your seat, waiting to know. So you see how nice to use a really bad disease state to infer something about a model. I think that's like one of the hopeful things you can do with diseases, right? So we're going to say the androgen in each follicle is bigger the follicle, the more androgen it makes. And I'm going to also observe that if you look at the androgen in the blood, which is basically made by all the follicles, it's just like estrogen is made by all the follicles. Androgen in the blood is made by all the follicles. And when you look at experimental measurements, unlike estrogen that goes up on those 14 days, the androgen stays kind of constant. That's an empirical fact. And that means, so if I say that androgen is some number times the follicle size, and the sum of the androgen is constant, so alpha sum of xi is constant. This is alpha x total. We get that alpha is this constant divided by x total. So that androgen, in fact, also goes like xi over x total. And the reason is that androgen production is regulated by FSH and LH. And estrogen shuts down LH and FSH. So the more total estrogen there is, the less androgen is secreted. So we finish with this beautiful equation where the race is only a function of your relative size. The race is run according to your relative size. The bigger you are relative to the other cells, the more you grow, but you can't be too big or too small. You have to be just right. And that's the secret of choosing 1 or 6 or 8, depending on this function phi. And that's what I want to analyze together with you. Yeah. So that's what we're going to do. We're going to look. Now it's going to be graphic. Okay, no equation, I think. So here is the relative size of the follicle. And here is this, is basically its growth function, phi. And we're going to plot it like this. And I'm going to call these two zero intersections. I mean, the amount of androgen you needed to start growing and to kill you, I'm going to call them 1 over M1 and 1 over M2. I want to choose M. And soon you'll see why it's convenient to call them 1 over M1 and 1 over M2. But those are numbers that have to do with how strongly androgen makes cells grow and die. This has to do with receptors and stuff like that. Now, I'm going to show you how you get this graph from this equation. And the idea is that we're going to analyze. So in humans, it's 1, but in mice, it's like 6 or 8 identically sized dominant follicles that ovulate at the same time from one ovary and the others from the other ovary. So what we're going to analyze is a symmetric solution where we have M follicles which are the same size and growing. So their xi over x total is 1 over M. Why? How do I know that? Because they're the same size So each one has a relative size 1 over m. If it's 2, each one has half of the total. If it's 3, each one has a third of the total. And the rest have died. So we're going to assume this solution, and then we're going to plug it into here. Okay? So our xi over xt, as I said, is 1 over m. And what's now the growth rate of these symmetric guys? It's 1 over m times phi of 1 over m. So 1 over m times phi of 1 over m. And if this phi is a positive number, they're growing. They're not only growing, this thing, we can call it v, and we have that xi equals vt. So we have, let's say, 1 or 2 or 6, whatever, growing linearly in time because of this relative size effect, where you can explain this linear growth. So if it could be 6 follicles or whatever growing exactly the same at the same velocity, and therefore reaching the end for day 14 exactly the same size. And that's actually very important, because if the mouse had a big follicle ovulating in a small one, the big one would have an advantage and the little one won't make it. Just like we know with sometimes twins in human beings, the big one eliminates the smaller one. So symmetry is very important here, and this symmetric solution guarantees it. I said that 1 over m, so that phi has to be positive. If phi is negative, so if 1 over m is here or here, it's not a good solution. And that you can already see that sets m. M has to be between. So in fact, m has to be between m1 and m2. So that 1 over m is between 1 over m1 and 1 over m2. So only m's between m1 and m2 get to ovulate. So it's 1 over m is between 1 over m1 and 1 over m2. When I invert it, m1 is larger. שפכתי את זה? כן. I think that's right. זה נכון? Because when I invert it, so if this is like, no, it's like, I remember it's like this because I probably wrote it wrong over here.
Yeah, you're switching the parabola.
You're right. Yeah, okay. So I just wrote it the wrong way. M2 is a big number and M1 is a small number, and they're set by the androgen receptor, whatever it is in the animal. And so M has to be between M1 and M2. And so you can, so that's already one way to choose the ovulation number, but there's another second more subtle task thing, in that is this solution must not only grow, it has to be also stable. What does that mean, stable? If I make one a little bit larger, I don't want it to take over and all the rest die. No, if I make one a little bit larger, I want it to return back home. So when does that happen? I'm going to say to you that if I'm to the right of the maximum, this region, if I'm here, then the solution is stable. How do I know that? If I make one follicle slightly larger, so it's more than 1 over m, it's going to grow a little bit slower than the rest, because this function is decreasing here, and therefore return. And if I make it one of them a little bit smaller, it's growing faster and it's returning. If on the other hand 1 over m was in this side of the maximum, if I make one of them a little bit larger, it's going to grow faster. The rest are going to grow slower, and this one is going to take over. And the symmetric solution is unstable. So only in this region is a stable region. Now, where is this maximum? If this is, I'm going to just approximate this as like a parabola. The maximum is in the middle of these 2 0 points. So m has to be larger. 1 over m has to be larger than the middle of these 2 points. So m has to be smaller than, this thing here is M1, M2 on the bottom, M1 plus M2 on the top, twice, right? Because I make mechane meshutaf, M1 plus M2. So this has to be smaller, actually, than 2M1, M2 divided by M1 plus M2. And if I think that M2 is very large, that's at this point becoming close to 0, just for simplicity. If M2 is very large, I can forget about this. M2 divided by M2 cancels out. This is 2M1. So I get a really simple formula for ovulation number. The formula is if this parameter is M1, it's again controlling the point where androgen becomes toxic. Then M has to be between M1 and 2M1. So, for example, if I want to have just one baby, it's between M is 1 and 0.5. If I want to have two babies, it's between 2 and 1. If I want to have three babies, M1 needs to be between 1.5 and 3. If I want 4 babies, it's between 2 and 4, etc. So for every M1, there's a certain range of ovulation numbers possible. So if an animal has M1 of 1.5, it can have either 2 or 3. If the ovulation number, on the other hand, is 0.7, if M1 is 0.75, it can only have 1. So just to summarize what we did here, what Michal did here, was take a look at the basic biology of this follicle growth. Follicles depend on FSH. FSH is inhibited by estrogen, which is the proportional to the total number, mass of follicles. So you have XI divided by X total. And then you need something to choose to prevent follicles that are too large or too small from growing, to make things just right. And then she identified androgen as this biphasic factor based on PCOS and other experiments. And that androgen is also relative to XI divided by X total, because it's also regulated by LH and FSH, which are inhibited by androgen, which is proportional to the total. And therefore, you get this beautifully symmetric equation where the race only depends on your relative position with this kind of bell-shaped function. And then you can restrict very much the possible symmetric solutions. There's also other solutions, but they're unstable. Or sometimes you can get twins with an unstable solution that's very, very slowly unstable. So there's also a possibility of a small possibility in this model to get twins or triplets, and the probability goes exponentially smaller for triplets, quadruplets, etc. Mainly you get one baby, one ovulation. You need fertilization and everything to get a baby, but one ovulation per cycle. So can this model explain familiar tendency for having twins? So Michal answers that it could be that this M1 and M2 can be different between different individual human beings. And twins in this model, I mean, there's two kinds of twins. There's identical twins where after ovulation, the growing embryo splits into two and you get two identical twins. It's rare. Actually, I don't know which is more rare. I think, yeah, identical twins are more rare than non-identical twins where you actually have two ovulations. And those two ovulations can happen in this model with a kind of unstable solution that would normally die, but they start so close that by day 14, they're still close enough. So it's like, if by chance the follicle started really close, and it's in fact it's one of, if we had infinite time, one would win. We only have 14 days. Sometimes the second one also makes it, the probability is very small because you have to have these two closed follicles, and that could be genetically determined because the M1 and M2 determine the probability of that happening, you can say. The bigger the stable region is, it could be that affects the probability of having two, like this unstable solution. Did I address the question? Yeah. That's actually very interesting. Okay, so fertility treatments. How does fertility treatment increase the chance for twins? So fertility treatments, I think the most common fertility treatment is to increase ovulation. So for instance, women that have PCOS, maybe reduced ovulation. One treatment is these androgen antagonists and agonists that basically what they do is increase FSH. They increase follicular stimulating hormone, X2, the driver of the race. The driver of the race. And that can break this delicate equation and cause the ovulation number to change. So you can have a higher chance for twins. And we can also explain PCOS quite elegantly with this curve. What happens in PCOS is that you have external androgen or more androgen in the body. And what that does, because this is the androgen axis, is shift this curve. And in the beginning, more androgen can actually increase ovulation chances, but once it pushes M1, you can say, so you're basically increasing M1. So this point drops 1/1. So by increasing M1, at some point, M1 becomes bigger than your 20 ovulations, your 20. And then M can't be bigger than M1. So adding androgen, we think, can explain in an elegant way what happens in PCOS. And that's like shifting this curve. And it could be that some fertility treatments shift this to the right, and then you get larger ovulation numbers. So you can begin to think about in this way about fertility treatments and problems in fertility and testable hypotheses, etc. The question is why twins and multiples are born early. That actually has to do already with the pregnancy stage. I actually am dying to do a lecture about the hormones in pregnancy. I mean, what could be more pregnant subject than that? But I'm not sure I'm ready. Don't know enough. M1, the question is M1 a local number from each egg? No, the answer is that M1, I mean, it could be, but the way we think about it is that M1 is a genetically determined sensitivity of all the follicles to androgen. So it should be the same for all follicles. And if you have a certain M1 and M2, it determines so follicles that are too large compared to the rest and too small compared to the rest, they die, and only a certain number, continue linearly in time as a stable, symmetric cohort of primary oocyte follicles destined to ovulate and give you the mice. Yeah. It is common fertility treatment, estrogen agonist. Okay. Okay. So Michal keeps on answering questions in the chat. She's really busy. All right. So just to summarize. How should we summarize this lecture? Is that the ovulation number is achieved by a hormone feedback that scales each follicle to the sum of all. And creates a kind of a private universe. No matter how big the follicles are, it's always by comparing to the others that you can choose the follicle number. And let's take a nice big sigh of relief. And I'll see you next week. So thank you very much.